Okay, so yeah, last time was mostly about generating functions in this property called rationality. So I think I'll avoid using that board. Okay, so the recap was this. You have this sequence, an, and if it satisfied a recursion, and the idea was this induced generating function now, a priori, this generating function would only be, say, integer coefficients formal power series. But if it came from a Fibonacci style recursion, then there was a way of manipulating it to see that, in fact, this would actually be a rational function, i.e., a ratio of polynomials. Okay, and we can say more generally that if you have any sequence, so the definition was if a sequence induces a rational generating function, then you say that the sequence has rational growth. And kind of the message was we want to explore the rational growth class and try to understand what kinds of sequences these are. Okay, so one thing to note about the rational growth class is that you can go the other way. So if you have something where you have a ratio of polynomials with rational coefficients, then by clearing common denominators, you can turn everything to integers. And once you have integers, you can, from this expression, you can write qx ax equals px. And let's think about what this says for a second. So this is precisely, if you unwind what this is saying, this is giving instructions of, for each term here, that's a shifted and scaled version of the original sequence. And so this is describing some linear combination of coefficients, and it equals a polynomial, right? So this is saying is everybody with me? Because hopefully from the exercises you played around and you saw this. So you get a linear combination of coefficients, which equals a polynomial. And then by taking successive differences of the polynomial, you can get down to 0. And this gives you a recipe for taking a finite depth linear combination of the coefficients equaling 0. In other words, you can work backwards to a recursion from here. Any questions about that? Does that square with the things you were playing around with yesterday? Okay, so this is telling you something really nice, that you can kind of go both ways in this correspondence. If you start with a bunch of integers satisfying a Fibonacci style recursion, you get a generating function in the rational, which is rational. And if you start with the data of a rational function, you can work backwards to a recursion on the coefficient. So that is a partial answer to the question, who cares what's good about rationality? But there's a little more. So let me, this may be well known to some of you, but it's really worth pointing out. So what we saw last time was for the Fibonacci example itself, we had that, let me write this as fib of x equals 1 over 1 minus x squared. Okay, well, you can do something pretty nice with this. You can decompose this by factoring the denominator, right? And so the roots of this are the golden ratio, and it's reciprocal. So this is 1 over 1 minus phi x, 1 minus phi bar x. Any questions about that? You just factor this. You get 1 plus or minus square root of 5 over 2 as the roots. And then we can sort of dig back into our traumatized calculus brains and remember that there's this partial fractions method for decomposing things. So you can write this as a over 1 minus phi x plus b over 1 minus phi bar x, or it's quite simple to solve for the a and b. I just did it a few minutes ago to make sure I'm not lying. And then what does this do for you? Something great, because now each of these gets expanded geometrically. And presto, it's a closed form for the Fibonacci numbers. Okay, so why? So looking at this, we can find the coefficient of x to the n as follows. I'm going to take the one from here and add it to the one from here, right? And over here, it's going to be a times phi to the n. Everybody see that? By geometrically expanding. And over here, it's going to be b times phi bar to the n. And so this is the nth Fibonacci number. Okay, and yeah, thanks. Still catching up on sleep. Right, so this gives a kind of excellent, historically accurate motivate. De Moivre did this, who's credited with coming up with generating functions in the first place. So this gives an excellent, historically motivated example of like just what rationality does for you. Once you have polynomial over polynomial, you can factor and separate and get sort of not just the recursion that tells you finitely much data seeds the whole sequence, but in fact closed forms and other kinds of fast computations. Okay, so rationality, good. Okay, and then let me remind you about this special class of eventually quasi-polynomials, which I claimed come up everywhere, and then Moira dutifully showed you come up everywhere. So recall.
Oh, we didn't prepare, okay?
Yeah, we actually didn't coordinate that. Okay, so just let me say it out loud. I don't want to write down the definition again, but the idea was that after some threshold time, the sequence will cycle through periodically polynomials, outputting values of the appropriate one in the sequence. Okay, so I'll just say after threshold time, okay, and the example that I gave last time was a sequence that alternated between 3n squared plus 5, 2n squared plus n plus 1, and n cubed. And I bring that back up just to say there's another way I want you to be able to think about eventually quasi-polynomials, EQPs. Instead of thinking of them as cyclically matching from a list of polynomials, I can think of them as a single polynomial with cyclically oscillating coefficients, right? Okay, so in this example, what would it be? Well, I'd take the degree 2, and I'd get 0, 0, 1, n cubed. I'm just using this notation for the oscillating coefficients. Everybody with me? Plus 3, 2, 0, n squared. Plus 0, 1, 0, n. Plus 510. Okay, just offering a different viewpoint on how to think about these. Okay, so the idea was, so you showed, perhaps, if you got to think about this, that EQPs are all in the rational growth class. Okay, so let's say out loud some of what goes into this. So there's lots of ways to do this. It's a kind of fundamental fact. But some steps that you can use to do this are you can show that xk over 1 minus x to the k plus 1 is the sum of n choose k, x to the k, and that these are a basis for polynomials. Okay, so to repeat, this rational function here gives you a power series whose coefficients are polynomials. And from those, you can just take linear combinations to get arbitrary polynomials. Okay, so this is a really succinct demonstration once you verify that these are equal, which I sketched last time. This is a really succinct demonstration that all polynomials are in the rational growth class. Is that clear to everybody? Okay, and then just from your exercises yesterday, how do you get from there to eventually? Okay, so now suppose something is spewing out garbage data for 100 values, and then it's giving the values of a polynomial, n cubed, after that. How do you see that that's rational? Anybody get this far? Well, think through it together. Yeah.
If you just sort of chop off the beginning where you have quasi-polynomials equals not eventually, so you get a rational function for that, and you just add in the polynomial.
Good.
You started with, you end up with a rational function.
Excellent. Cat, right?
Yes.
So I had 100 garbage values at the beginning. So I can like sort of pull those aside as a polynomial of degree 100. That's a part of this power series that just goes finitely many places. A power series with finitely many terms is a polynomial. Okay, so I can rewrite the thing with early garbage as a polynomial plus a beautiful thing that is n cubed forever, right? And so a polynomial plus a rational function, well, I just combine them with a common denominator and it's a rational function. Does that make sense, everyone? That's how you handle the eventually. How about the Kwazii? Let's put the Q in EQP. Okay, so suppose something alternates between, this was an exercise as well. Suppose something alternates between matching the values of two polynomials. What can I do with that? Let me be concrete. Let's just write down a quick example. Let's take 3, 4, 3, 4, 3, 4, which alternates between outputting the values of two constant polynomials, 3 and 4. Okay. What do I do to sort of efficiently write this as a rational function, as corresponding to, as associated to a rational function, the coefficients of a rational function? You can split it. Yeah, so there's a way to get the all 3 series. The all 3 series is 3 over 1 minus x. Everybody see that? That's the all 3 series. The all 4 series is 4 over 1 minus x. Okay, good start. Now what?
Does it need to be like an x squared?
Yeah, if I square something, something good will happen somewhere. Okay, yes. So in particular, if instead of squaring the whole denominator like I was doing there, if I just put the square here, what happens? 3 over 1 minus x quantity squared. Well, now here what happens is this becomes the sum of 3 times x to the 2n. In other words, it's only got the even exponents, x to the 0, x squared, and so on. So actually now, this gives me those 3's. Does everybody understand that? You see why putting in the square did a good thing there? Okay, now if I do the same thing here and I put in a square, this is going to give me those 4's. Now I want to shift it over a place. So what do I do to shift it? Yeah? Go ahead. Yeah, there, it's shifted. Everybody with me? Or her? Good. So now this checks off the 4s, and now I add them, and hey, look, they had the same denominator already. That's nice. So I get 3 plus 4x over 1 minus x squared, and I hope that suggests the recipe for how to do all EQPs. Okay, everybody happy? Good. One more little word about the kind of big picture, the who cares piece, the how does this all fit together, before I go on to new kind of more geometric stuff for today. So a few people were asking like a really good question. Yeah, sorry, I won't use that board much, and I'll put it up top in a second. Which was, what does this have to do with rate of growth? Because those of us who have thought about growth of groups in particular before are like trained electroshockily to only think about growth rate, how fast things grow, right? Well, so the point that I want to make here is that this rationality is kind of an orthogonal property. So there's two questions you can ask about growth. Well, there's lots of questions, but one question is how fast. And I want us to think about rationality as kind of on another axis that asks how regular. Okay, so let's put rational here and not. Let's put fast here and slow. And just kind of convince ourselves that things can live in different places. So, I mean, by slow, in context, let me mean bounded above by a polynomial. So in the polynomial range, bounded above by a polynomial. And by fast, let me mean, for now, at least exponential. And rational and not. OK, so just humor me for a moment. Let's fill this in. So what's rational and slow, for instance? Polynomials, sure. Or like, you know, constants. So yeah, but let's say constants. You know, like, say, 1 over 1 minus x, right? So that's a constant sequence, for instance. What's not rational and still slow?
Pi.
Yeah, the digits of pi sequence. 3, 1, 4, 1. Not rational, but it's bounded by, you know, 10. It's not growing very fast. It's not growing. Really? Now, how about fast and rational? Yeah, so the 2 to the n example, which corresponded to 1 over 1 minus 2x, right? This corresponds to 1. And then how about fast and not rational? Yeah, so we did this example, which was the Taylor series of e to the x. But what does that look like? That looks like x to the n over n factorial. So actually, the coefficients aren't growing very fast with that, are they? But I can do something silly. 2 to the n plus digits of pi. Right, so I can take the nth term to be 2 to the n plus the nth digit of pi or something like that. And I hope this really, actually, it's a dumb example, but not so dumb. Because I hope it really illustrates this is boundedly close to one of our prototypical rational examples. It's very fast growing, but it's got this transcendentality baked in. And so what I hope this is illustrating, so let me put this up so everyone can see it. These are really kind of different ways of thinking about growth. Yeah?
So this is power series, but like what's a group in a generating set?
Yeah, oh yeah, well we're going there. So yesterday was general mechanics with these generating functions and rationality. Today I'm going to introduce some geometry, and the last 2 days I'm going to bring it to groups. But you would like a preview, perhaps? Yeah, so I'm going to give you examples of of groups with polynomial growth that are rational and not. There are also groups of intermediate growth. In between, there are groups whose growth rate is like e to the square root of x. So it's intermediate between exponential and polynomial growth. And those, for reasons I'll explain shortly, can never be rational. Okay, so that actually is an interesting connection between this axis and this axis that I'll come back to. And in the exponential growth class, I'll tell you more. But within group theory, the known non-rational examples are very, very few. But I can talk more about the suspected non-rational examples in groups. OK, that's a preview. Any other questions about this right now? Cool. All right. So let's talk about something completely different. Instead of Euler, let's switch to Gauss. All right, so I want to tell you a little bit about one of my favorite problems. It's called the Gauss circle problem. And it goes like this. So it's a counting problem, just like these other counting problems we've been doing, in that you count. And it's defined as follows. So I'm going to say G for Gauss, sub D, D for disk. This is the unit disk in R2. Of n equals, by definition, the number of lattice points in the n times dilate of the disk. OK, all I'm doing is counting points in the disk. So the picture looks like this. Here's my unit disk. I'll make it closed. I'll make it the closed disk. So what is GD of 1? That asks the question, how many lattice points are in this picture? And the answer is 5. Everybody got it? And then for GD of n, I take radius n and count. OK. So how many? Well, I hope as you ponder that while I erase, you're thinking about it kind of in those terms over there. So there's how fast, and there's how regular is this growth. OK, so first question, how fast? So about how many lattice points are there in the disk radius n? And tell me why you think so. Yeah, right? So who said that? What? N squared-ish? Yeah, OK. And I was hearing a little more detail murmured from somewhere. Yeah, like pi is more detail, yeah. So this is something like pi n squared. OK, so you were saying n squared because you were thinking of. That's an actual question. It didn't sound like it, but.
Yeah, quadratic squares.
Yeah, quadratic squares. What about the picture? Makes you feel like it should be quadratic?
Looks like a plane.
Looks like a plane? Yeah. There's like. There's the dimension is 2, right? OK, and why pi n squared? Because it's like the area. Why should the number of lattice points be proportional to the area of the disk? Does that seem reasonable? Yes, voguing tells us everything. Yeah, right, because if you think about the grid of lattice points, which should go through those, then there's roughly 1 lattice point per square. You could, in fact, if you staggered the grid of squares so that they were centered at the lattice points, then there's really roughly 1 lattice point per square. Or you could just assign squares to their sort of southwest lattice points or something like that. And so that tells you there's roughly as many lattice points as there are unit squares, i.e. roughly the area. And that's what Gauss thought, too. And where that goes wrong is around the boundary, you get some sort of fuzziness, because you get partial squares contribution to area, right? So Gauss told us that this number should be pi n squared plus something on the order of n, because that's the length of the boundary. It's linear in n. And so that's sort of the number of affected squares grows like n, or like, 2 pi n or whatever. OK. If you're not comfortable yet with big O notation, then talk to us about it in the problem session. Really useful. OK, so that's nice. And it took about 100 years for Sierpinski to do a little bit better. So Sierpinski showed that actually this number is pi n squared plus an error term that's a little smaller. You don't need all of the linear error term. You can actually get away with n to the 2/3. And you might think, how important is it that this is actually a circle? And Sierpinski's student, van der Korpet, proved the same result for sufficiently smooth boundaries. Of course, instead of pi n squared, it was area times n squared plus an error order of n to the 2/3. And if you think about this, this is basically the Riemann integrability of the region. It's saying that the boundary makes a lower order contribution, and it's kind of quantifying that. OK, questions about what I've written so far? Yes?
For the second statement, are there conditions of convexity or symmetry or something? Because I can take a region that just doesn't go through any lattice points. You shouldn't know that, right?
You can take a region that doesn't go through any lattice points. But as you grow it, so what we're doing here is we're dilating it. Yeah. So yeah, no, but good point. So you might start with some like sort of region that winds around and misses lattice points, but you're fattening it up fundamentally when you dilate it. And it can't dodge all them lattice points forever. OK, questions? See what's going on? OK. Well, I can write down the sequence of numbers. And I can think about, I know how fast it grows. I know something about how fast it grows. Actually, I should tell you the Gauss circle problem conjecture. So for a long time, people tried to get this error order down lower than that. So in particular, you can write that the exact number is pi n squared plus some error term, just to the correction term, an error term that depends on n. And then you can ask what the best power law is for this. So you can define p of n to be the log base n of the error, right? So that should be detecting the power. So Gauss showed that this was at most 1. Sierpinski showed that this was at most 2/3. It is universally conjectured that the actual power is 1/2, and I should say limits to 1/2. So in other words, phrased differently, the Gauss circle conjecture is that the this number is pi n squared plus something on the order of n to the 1/2 plus epsilon for any positive epsilon. A result of Littlewood and maybe Hardy, Littlewood and a collaborator who shall remain unnamed because of my memory, shows that this is best possible. N to the 1/2 isn't true. So that's pretty cool.
And the conjecture, is that a lim soup? Because I had also.
The conjecture is just that it converges.
Oh.
Yeah. So about 7 or 8 years ago, a paper went up on the archive claiming to prove this, and then it took like 5 years to get withdrawn, I think. So this is still an open problem and a really interesting one. And actually, it's amenable to the polynomial number theory that's been seeing like unbelievable breakthroughs in the last few years. So I wouldn't be surprised if the days of this conjecture are numbered. Okay. Okay, so then we can wonder, any chance of rational growth here for this? And what I hope is that it doesn't feel rational to you. Having now played around with some examples, just the presence of pi might make it feel like it shouldn't be rational. And so the last comment I want to make about this for now is that you'd be right. This isn't rational. And the way that this can be proved is using one of the only tools that we have for establishing non-rationality, which is a remarkable theorem of the number theorist Michael Stoll. So here's what he showed. He showed that if you have a sequence whose growth is like alpha times n to the d, in this case that's pi n squared, this squiggle is that the ratio goes to 1, right? It's the usual kind of growth rate squiggle. Then if alpha is irrational or transcendental, so is the growth. That's very cool. So if alpha is an irrational or transcendental number, then the growth is 2. Okay, that's just sort of shorthand for saying the growth is also irrational or transcendental. Okay, great. So now we have a geometric counting problem with non-rational growth. So I think of this as round counting. Like I said, the generalization from van der Korpit uses smoothness of the boundary. I want to contrast it with what I call pointy counting. So let's do almost the same thing, except instead of a disk or something smooth, let's use polytopes. Let's do lattice point enumeration in polytopes. Okay, so let me take P to be an integer polytope. By which I mean the vertices are in the lattice points. Vertices in Z to the D. Then I can make exactly the same definition. Can define this kind of enumeration function. GP of n is the number of lattice points in the n times dilate of P. Well, no problem, once again, about the growth rate. So under this definition, it's easy to see for the same reason that GPn should grow like the volume of the polytope times n to the d. Does that make sense? Yeah.
So this is in R to the D.
Yeah.
Like,
Mm-hmm. Yes, thank you. Yeah, and okay, if I want this to be, well, so if the polytope is itself lower dimensional than the space, then let me not allow that. Because then it'll have no volume. This will be, yeah, let me not allow that. Okay, so I want the polytope to have interior. All right. So that's nice, but we can sort of expect, again, from the feeling of it all, that this has a much better shot at rationality. Okay, and that's actually what happens. So to build up to that, let's consider the two-dimensional case. In the two-dimensional case, we have a very powerful tool working with us when we want to approach this, and that tool is called Pick's theorem. I don't know if you've seen this before, and you will prove it this afternoon. But it's a beautiful theorem that only works in dimension 2. And the theorem is that for lattice polygons, the area is the number of lattice points on the interior plus half the number of lattice points on the boundary minus 1. So this is area. This is interior points, i.e. lattice points. B is boundary. Okay, you'll play around with this. It's really kind of fun and hands-on.
Is that in like Z squared?
Yes, but let's do an example. Yes. So this is lattice polygons, i.e. polygons with vertices in Z squared. And these points are Z squared points, are lattice points. Yeah.
is it convex?
It doesn't have to be convex. Check that that's true. Okay, so let's do an example. Let's look at the square with a vertex at 2, 2. Okay, so the area here is 4. The interior points, I is the number of interior points. So what is it? Just 1? Make sure that I'm doing this right. This is you. The number of points on the boundary is 1, 2, 3, 4, 5, 6, 7, 8. And 1 plus 4 minus 1 is 4. Huh. Something good just happened. Okay, any questions? One plus 4 minus 1. Yeah. Yeah.
Do you only allow for contractible surfaces, or you allow for any kind of?
No, any kind of topology. And actually, as soon as I get to the statement of how this works, you'll see how much generality it is. So all I require, in fact, I should just say, I can do this enumeration for any region. For any region at all, I can certainly consider this counting formula. This is just a definition, the number of ZD points in n omega. What's special about polytopes is coming up. So there's a theorem that tells us what the answer is for polytopes that I haven't stated yet. But this is defined actually for any region at all.
Any region with the same dimension as in?
Actually, this is defined for any subset at all. Right? This is just a definition for any subset. Whether you can say something about it requires some hypotheses on omega.
Probably the asymptotic estimates for any region with non-empty.
You need Riemann integrability.
Region like.
You need, yeah, so that's precisely what you need, as it turns out, to make the, okay, but let's move on. So, so this is my setup, and let's note that from Pick's theorem, we can solve this problem for lattice polygons. Okay, so what do we want? Well, we want GP of n for lattice polygons. Okay, polygon means I'm in 2 dimensions. Well, what is that? As I said, we're thinking of these regions as closed. So this is the number of interior points plus the number of boundary points, right? Well, I have A equals I minus B over plus B over 2 minus 1. So I have A plus B over 2 plus 1 equals I plus B. Everybody happy? You should be checking me. Does that look right?
Minus B over 2?
No, I wanted to add B over 2 to both sides, but thanks for checking. Okay, everybody happy? Great. So, let me write this as IN plus BN, right? This is the number of interior points of the nth dilate plus the number of boundary points of the nth dilate. Everybody see what's going on? Okay, but let's use this formulation and see what happens when you scale. Now, I'm going to just take the case that I'm scaling by integers for the moment. So let's imagine that n, in fact, let's take n to be a natural number and see that we can get something really nice. Okay, so when n is a natural number, what is the area of the n dilate? Well, it's whatever the area was of the original times n squared. That's how area works. We happy with this? Okay, but now let's think about I of the nth dilate and B of the nth dilate. And here it really matters that we're dealing with a natural number. Here it didn't. But when we have a natural number, let's think about what happens. So if I had one of the edges of the polygon and it went through some vertices, and I multiply it by 3, Well, that rescaling by 3 is going to, first of all, send its endpoints to other lattice points, first of all. Right? And it's going to scale the number of points linearly on the edges. So you can think about this more later, but this is at least for now a heuristic. So what happens to the number of boundary points is that it scales by n. What happens to the number of interior points? Yeah, so this should do something like n squared I. And what happens to 1 is nothing, right? 1 doesn't scale. So you can put these together to get some nice form. Actually, I didn't even need this, right? Because all I needed for I plus b was this expression. So what do I get? I get n squared a, which I'll write as a n squared, plus n b. Did I do this right? Plus n over 2 b plus 1. OK, everybody happy with that? I just took this formula and I plugged in the sort of modified versions to get this answer. And let me rewrite this as b over 2 times n. With me? Cool. Something great just happened. Mystery, confusion, intrigue over centuries. A polynomial. Right? There's no kind of error order to think about here. We have an on-the-nose polynomial. OK, and I want to make a few observations about how amazing this is. Try to drum up kind of disbelief. So one thing that's remarkable is that polynomials are, of course, continuous in their input variables. But this is a count of a number of points. This is a fundamentally discrete thing on the left. This would be an a priori continuous thing on the right. But I've only thought about it kind of by using discrete data. So what I have here is that this discretely varying thing and this continuously varying thing agree at all natural number input. OK, anyway, this is pretty cool. Seems to me. That's 2 dimensions. How about higher dimensions? First, the bad news, there's no Pick's theorem. So Pick's theorem doesn't generalize to higher dimensions in the following sense. There's no formula that relates the volume of a polytope to just the count of lattice points on the faces of different dimensions. And one way to convince yourself that that's true, let me do a literally hand-waving argument. So think about R3, and think about in the xy plane, take a square, a lattice square as the base, and then take a pyramid on that base of a certain height. Right? You guys see what I'm doing? Well, if you pick a height that's right above one of the points on the base, then you'll get some lattice points on the boundary. And if you pick some other height, you won't. Those have the same volume, because the volume is, what is it, 1/3 base times height, maybe? Something like that. They have the same volume by Cavalieri's principle. So I can change the volume without, so I can not change the volume while changing the lattice point count, right? Which should convince you that Pick's theorem doesn't generalize. All right, so maybe we're depressed. We had this really beautiful thing happen, but it was a fundamentally 2-dimensional phenomenon. So the bad news and the good news is called Earhart polynomials. And this feels really magic to me still, even though I like to think about these. What Earhart, so the theorem of Earhart, who was a mathematician who, as I understand it, proved this in the 70s, returning to research after having left research and become a high school teacher, and then sort of came back and proved this gorgeous theorem. And the theorem is that for a lattice polytope, P not necessarily convex, that the enumeration equals a polynomial. This is amazing. So it's a d n to the d plus a d minus 1 and d minus 1 plus del to e1 n plus a naught. A polynomial on the nose. Not just polynomially growing, a polynomial, the genuine article. And if we look at this and inspect its coefficients, we might suspect that its coefficients are encoding something about the geometry of the polytope, and they are. So we know what this one's encoding. This is the volume of the polytope. What do we think this one might be doing? In particular, I feel like it's gazing at this can kind of help us think about that. It's some sort of boundary, right? Notice how those interior points didn't show up here. It's just the boundary. So yeah, this is like an appropriately normalized surface area term for the polytope. And if you're interested, I didn't write problems about this, but I can tell you more about how to think about the area term. But really, I hope this feels like it's the right kind of thing. And here's this non-convexity in action. This is actually the Euler characteristic, which is kind of awesome. So yes, it can have topology. When you play around with this and you do some examples, keep in mind this is the Euler characteristic of the polytope as a filled-in object. So don't forget that top dimensional face when you're playing around with examples. Any questions about what's going on here? Okay, and then of course you want to know, what about the other coefficients? And so do I. It's actually a pretty big, some of what's going on with the other coefficients I call numerology. It's kind of a mystery how to extract the geometric information from the coefficients. Some more stuff is known, but a lot is not about what the other coefficients mean. Questions? Yes?
We don't just have to do with like the lower dimensional faces?
Right. They don't in an obvious way, just have to do with the lower dimensional faces. Exactly. There are, if you get interested in this, as I hope you should, then Jamie Pommersheim and his collaborators have a bunch of papers where they look at kind of what these coefficients mean in special families of polytopes. But in general, it's pretty hard to describe. Okay, so that's the contrast I have in mind. So now we've looked at some geometric counting problems, and we've seen that round counting and pointy counting kind of behave differently. Yeah?
I'm thinking about like approximating circles with polygons. Like we
Right.
have very opposite behaviors, but there's like some limiting thing that's happening, right?
Yeah, I mean, it's kind of back to this worldview over here. Yeah, approximations are nice, but when we're studying rationality, right? So these are all in the rational growth class. When we're studying rationality, approximations get us like exactly nowhere.
Yeah.
So that makes this theorem really powerful. Yes?
Can I hear about ad hoc quasi-polynomials?
Yes, you can. That's next.
Polynomials coming.
Yeah.
Too much.
Yes. So Earhart says a little more. Earhart says, oh, okay, so this was a lattice polytope. I don't know if he actually said, oh, okay, but I'll be Earhart. So this is a lattice polytope. What if instead you just had rational vertex coordinates? Okay, so then the sort of theorem prime is for a rational polytope. The enumeration function is a quasi-polynomial. So let's do an example, because this is actually quite nice, I think. So let's do the example of the half square. Okay, so let's take the square with a vertex at a half, and at the origin, and let's actually just count. So what happens if I do, so let me call this square S. So what happens if I do G? Actually, you know what? Why don't I make my life a little nicer? Do I want to make my life nicer this way? Well, sure, okay, fine. I'll leave this square. So let's do G even number, GS even number. Okay, what happens for GS even number? Well, then I have the square with a corner at 0, 0 and a corner at KK. So I can get its exact number of lattice points, which is K plus 1 points along the bottom from 0 to K. K plus 1 points along the side, so I get K plus 1 squared. Everybody happy with that? And then what about GS 2K plus 1, the next number? Right, I tick it up one notch. Any more lattice points? No, it's the same. So that means that GSN is alternating between the polynomial n over 2 plus 1 squared if n is even, and the polynomial n minus 1 over 2 plus 1 squared if n is odd. So it's a quasi-polynomial. Any questions? They come up everywhere. They kind of do. OK, but what this tells us, and thanks, I did not plant that question with Tusa. But what this tells us is that, in fact, enumeration in rational polytopes is in the rational growth class. And that is useful. There are exercises to get you to play with this. Glad you asked. Anybody have a hunch of what the period should depend on here? I mean, here the period was 2, right? Yeah, so there are these denominators going on in the vertex coordinates. And if you take sort of the least common multiple, you'll play with it. Okay. Okay, so I have a few minutes left, and this is what I wanted to tell you about these geometric counting problems. So instead of going on to groups, what I want to do is go back for a moment and talk about something that was addressed last time and use the last few minutes to say a word. And so what that word is going to be is more info from the rational expression. Okay, so we've already seen that there's some information in the rational expression that's recorded in the denominator in various ways. The denominator is telling you about the terms of the recursion. And now I want to point out that you get actually strong information about the growth of the sequence from the location in the plane of the poles of the denominator. Okay, so that's the claim. So let me just sort of walk through this for the next minute or two and leave you to think about it a little bit more later, but this is fundamentally important. So let's think about our two different kind of prototype examples, 1 over 1 minus x versus 1 over 1 minus 2x. And let's think about what's going on that's different. Well, here, so poles of an expression are of a rational expression are the roots of the denominator. They're the places where the expression blows up. So here, if I plot this, let me plot it in the complex plane. If I plot the pole here, it's at 1. And here, the pole, I'll sketch the unit circle as for reference. Here, the pole is at 1/2. OK, and so the claim that I want to make in the last couple minutes is that poles on the unit circle or poles inside the unit circle cause very different behavior. OK, so, well, one thing to notice is that having a pole inside the unit circle means that the coefficient here has norm bigger than 1 if it's a linear expression. And so that means that it grows exponentially when you expand this. Does that make sense? So that gives us a kind of indication that we should expect exponential growth when we have a pole inside the unit circle. Now let's take a little bit of thought for poles on the unit circle. And in particular, there's a special kind of pole on the unit circle that this is one of that I want to explore for a moment. Sometimes, frequently, the poles will actually be roots of unity. So they'll be values like 2 pi I over 3, for instance, which have the property that when you raise them to an integer power, you get 1. So this satisfies x cubed equals 1. OK, so these are called roots of unity, and the 2 pi I over n. Sorry? Yeah, thanks. The e to the 2 pi I over n are the primitive roots of unity. OK, so with the last minute of this lecture, let's take a moment and think about what happens if we have an expression with pole a root of unity. OK, so let's think about that. So what if I have 1 over 1 minus zeta n x, where zeta n is e to the 2 pi I over n. What happens? Let's expand this geometrically. Victim I haven't heard from yet. Talk about what happens when I write this out. So geometric series expansion. Get me started? Yeah? Mm-hmm.
Okay, so I guess it cycles through the powers of that, so it goes
Yes.
like each k over n for each
Good.
each integer k less than n.
So when you say it cycles through, you mean I get 1 plus,
e to the 2 pi I over n.
right? I will lazily write that zeta n, x plus.
And then squared.
Yeah, exactly. I get, and my zetas are going to start looking like c's. OK, good. And then the observation was that what happens when you take a root of unity and you raise it to powers is that it wanders around the circle in equal angle increments. And if it's an nth root of unity, then after n steps, it comes back to 1. Is that clear, everybody, from the picture? OK, so what does that mean about these coefficients? That means that these are actually periodic. OK, so there's something nice to notice, and I'll stop this lecture here. So if you have poles inside the unit circle, that forces terms with norm bigger than 1 in the coefficient of x, which creates exponential growth of the coefficients. If you have all your poles on or outside the unit circle, that won't happen. And actually, there's an exercise from yesterday, which is really fun if you didn't do it, to show that that forces you to stay in the polynomial growth range if all your poles are on or outside the unit circle. In particular, root of unity poles are gorgeous because they give you some nice periodicity. OK, and so I'll just end on the punchline. That explains this kind of mysterious middle range here. So if you have poles inside the unit circle, you grow exponentially. But if they're all on or outside, you grow at most polynomially. Right? And that's actually a proof that rationally growing sequences can't have intermediate growth in between polynomial and exponential. OK, so that gives us our kind of first relationship between this axis and this axis. Any questions about that? Great, then that's a good place to stop. Thank you.